This is the last lecture on linear regression for Stats 253, Chapter 10. The previous lecture was more of a conceptual idea about prediction and estimation. This is a lot more specific in this lecture. I want you to know some of the things that I'm going to talk about here. The other was more, not quite FYI, but just about for your information. Okay, so now once you've made a least squares fit, you've now got to evaluate the line that you made, and we're going to use three parameters. One is a coefficient of determination, the other is a standard error of the estimate, which we looked at previously, and we'll look at that again, and the other is the behavior of the residuals. Now the coefficient of determination is written as R squared, and you know R previously as the correlation coefficient, and it's true, you can compute the coefficient of determination by just taking the correlation coefficient, which you computed previously, and squaring the result. There is another way to compute the coefficient of determination. We're going to look at this other way to compute the R squared, not because it's necessarily a better way, but because it explains some of the terms that you will see frequently in least squares fits. All right, the first is, here's your data point and here's the line. The distance from the data point down to the line, remember the vertical distance, is called the residual or the error. If you calculate all these residuals, which would be yi, data point minus the point on the line, if you calculate those, square them and add them up, you have SSE, sum of the squares of the errors. That's only going from the line, from the data point down to the line. If you take the line and you go down to the average value of y, this is the mean value of y. So this is y mean, which means you took all your little data point, the y values of the data point, and added them up and divided by n. All right, that's just a line drawn through that value of y. Here's your y bar right here. If you take the vertical distance from the line down to the mean, okay, that's the sum of the squares. Okay, forget the r here for now. So I've got y hat minus y bar, you're squaring it, you're summing up, squaring it, and that's SSR. Okay, SST, T for total. All right, I'm going to take the data point down to the mean. How far is each data point off the average? And obviously you can see these distances add up. The total here is the sum of from the data point to the line, line down to the mean, data point down to the mean. Okay, let's go and look at these terms a little bit more. The SST is the sum of the squared total distance from the data point down to the mean value of y. So if you can't read that, I'll write a little bit bigger. This is your total. You're going from the data point down to the mean value for y, squaring that term, that distance, and adding it up. That's SST. SSE, we did that before. That's the data point down to the line itself. Okay, this is called error not explained by regression. Now the R here, SSR, means sum of the squares of the, well, regression has to do with the regression, because this is called the error explained by the regression. Again, error here is in quotes. Is it wrong that something's not at the average value? I don't think so, but that's how the word error is used here. It's not, that's how it's used. Okay, it doesn't mean it's necessarily wrong. What if everything came in on its average value? It'd kind of have no results at all. So if you just look at this, okay, here, whoops. So here's the total. yi minus y bar equals yi down to the line. okay, plus okay, obviously these are gone and it's just algebraic. All right, I wanted to put these up here and go through this so that you would learn, you would be able to see these terms. A lot of reasons you take these introductory classes, or the reasons they make you take these introductory classes, is to learn the terminology and the notation. You don't get to learn all the derivations, you don't learn why, and you don't get real proficient at doing the calculations. That comes later. So here is the promised second way to calculate the coefficient of determination. So here's our R squared. In the numerator is the sum of the squares of the error predicted by the regression. That is the distance from the line down to the mean, divided by the distance from the data point to the mean. Of course, using the identities, you can write this a little bit differently. You can write it as 1 minus, this is the sum of the squares of the distances from the data point to the line, divided by the sum of the squares of the distances from the data point to the mean. Okay, now this R can vary from 0 to 1. If it's 1, it's a perfect linear fit. It could be, by squaring it, you've lost the information from the coefficient of the correlation coefficient that the line will be sloping upward or downward. Okay, so 1 means it's perfect linear correlation. Could be inverse, could be direct. You don't know that from the R squared. Right? In what case is this completely 1? All right, when this numerator is 0, the numerator is 0, that's the distance from the data point to the line. If this is 0, that means the data points are right on the line. Okay, and if all the data points fall on the line, that means that there was perfect linear correlation because the data points already lined up on the line. So you can kind of see that. And there's different ways to have zero correlation, so we don't have to go into those. Okay, and you can write it out in terms of variables here if you want to see it that way. So here's your SSE is from the data point to the line. SST is from the data point to the mean. And the SS part means square them and sum them up. Okay. So that's your coefficient of determination. The correlation coefficient was calculated before you even knew the line. Here, by writing things in this way, you calculate this coefficient of determination after you have the line, because you need y hat in the equation. Now, for the least squares fit, we had several assumptions. The first two we used to find values for the slope and the y-intercept so that we could write the equation for the line. And the first assumption is that the sum of the errors or residuals is 0, and the second is that the sum of the squares of the errors or residuals is minimum. Now, another assumption of linear regression is that the standard deviation of error is the same at every value of the independent variable, and this is easier to see graphically. For the data sets we've looked at where you have 5 or 6 points, this you can't even see this effect. This effect shows up when you have many data points, like 100,000 or something. So we have a value of x. This is a value, this will be at a measurement point, and if we look up in y, now this is slanted over to the side. You see that this is slanted in order to show you something. Okay, then you would have all sorts of data points, all sorts of values of y associated with this value of x, because you have many data points. Now they're going to be kind of, just drawn a few here. The idea here is that your linear regression comes through here and will hit the mean. If I took all these y values associated with the x, found their average, that would be right here and it would line right up on the line. Now, of course, there's going to be some spread in the data. We assume that the data is distributed normally. So there is a nice bell-shaped curve we can draw, right? And if we draw this bell-shaped curve, if you remember previously, if you go a couple standard deviations either way, you should have most of the data points. For example, you'd have about 95% of the data points if you went 1 or 2 standard deviations from this mean. So here you have all your data points. They have a mean, let's call it mu, for that particular value of x, and there's a standard deviation for that particular value of x, and I could draw a little bell-shaped curve, and most of the data points would be there. Let me erase this so I can put my data points in better. Let you know what I'm sort of doing. Okay, we've got data points all along this line right here. The majority of them, here's the average one, the majority of them are all clustered right in here, and there's a few that are kind of out here. All right, but most of them are right here about the mean, so you could draw this nice bell-shaped curve, and the bell-shaped curve here is representing the number of data points. So there's almost no data points really far from the line, and most of the data points are clustered by the line, and the line goes right through the mean for the y values for that particular x. Now you go to another value of x, you've got data values again along this line right here. Again, remember it's slanted to show you this effect. They're going to be normally distributed. Most of them are going to be clustered right here about their mean. The mean is where the line is coming right through that mean, and there's only a few outliers here. Now this assumption is that it seems like a lot to assume, but you're assuming you have a lot of data, they're clustered about where you're going to draw the line is coming through their mean, and each one has their own standard deviation, and you assume that the standard deviation for this value of x and this value of x are the same. Now, in other words, how far the data is spread away from the line is about the same for every, well, it's exactly the same for every value of x. This is an assumption. In other words, do we always meet these assumptions? Well, we try to get close to them because this is data, and there's always, as they say, noise in the data. Okay, we're assuming that all those are the same and we can actually calculate them. That means we take these, oops, I need the marker, the sum of the squares of the errors, which is how far the data point is from the line, squared up, divide by n minus 2, because that happens to be our degrees of freedom here, take its square root, and we saw this previously when we were looking at those confidence intervals. That is the standard deviation for the error, and we assume that it holds at every data point. Okay. Now, a lot of these I'm not asking you to calculate for homework at all. There's only so much you can do in a semester. But this next part on the behavior of the residuals, you have to do that, and you will do it by calculating some graphs in R and looking at them. R will give you the residuals. Go look at the tutorial for R and linear regression, and you'll see that there's some information there for you. Okay, what we're looking at is the behavior of the residuals, and this is another one of these gestalts. This is another look at something as opposed to calculating something. Although it can be calculated and graphed, we're going to look at it. All right, so what we're going to do is plot all the residuals. We'll take the data point and we're going to plot them. All right, and they're going to be all over the page. We hope they're going to be all over the page. If they're all over the page and it appears that the residuals are random, then we say the graph exhibits homoscedasticity. Okay, it said homoscedasticity like the S and the C. You want to say scedasticity, which would be more fun to say, but it's supposed to be homoscedasticity. All right. If there's a trend, then this is bad for a linear regression, and it's called heteroscedasticity. All right, let's take a look at that. Now you can plot these residuals against different values. But what you want to do what you hope to have is something that comes out like this. What does this say? This says that my residuals are that there's no trend in my residuals. They're all just about as bad at one place as they are at another. And remember, residual is the distance from the actual measured data point down to the line. And this is the this is what you want to see. Now let's look at what you don't want to see. All right, this is what you don't want to see. What's the residual here? Well, it's actually, at least on the scale of this graph, these are pretty close. You would say in this range, this would be some value of x, let's say, in this range, your linear fit was pretty good. Your data value, your residuals are just, you don't see any real trend. Now look over here. It's way off. Your residuals are humongous here compared to some other part of the graph. What this probably means is that your it wasn't a linear fit. You made a linear fit where you should have made a quadratic fit or some other kind of polynomial fit. Right. This is what you don't want to see. This is no good. But if you see it, that's just information. Why would you get something like this? Probably because you did not look carefully at your correlation coefficient, your R, and your scatter plot when you started. If something like this happens, the data was most likely not a candidate for a linear fit. The final topic I'm going to present in this video, in fact this is the final video for linear regression. You could have a whole class on it at some universities, and you can get entire classes just on linear regression. So we do it in one chapter here. Okay, well, this is your introductory class. You'll get more of it if you go on in statistics. So what are we looking at here? Outliers. We've talked about outliers before when we talked about box and whisker plots. Now we're talking about them with this linear fit. Outliers. Outliers are data points that can, if they change the linear regression line, they're called influential observations because they have an influence on what we do. Now, thanks to software, you can exclude some of those data points and see what happens. I mean, if you have an outlier and you still have the same line, it doesn't really matter. That data point can just sit there. But if that outlier has pulled your line into a new slope, okay, then it's changed what you're doing, and you must carefully consider if that's something that you want to allow. Okay, here's an example. All right, we have this outlier here, or this data point here. Now, when this data point is included in the calculation, the least squares line looks like this. This is with the outlier. Right. Take that outlier away, and what happens to the line? It becomes a solid line. You see how it's an influential observer? It changed the line. Now, if you have, say you had more outliers down here, perhaps it wouldn't matter. But with software, you can take that off and take a look at it and see if you and see the results. Okay, so that's it on linear regression. Again, you can take entire semester-long courses using R and linear regression. If you look up Stanford's course offerings in statistics, you'll see that there's one there using R and linear regression. So there's a lot more to study in the subject matter. I hope I've given you some of the terms that will be useful in the future. If you have questions on the homework, you can contact me.